Hey everyone, I'm Julius and I'm back with some new in-depth explainer animations for you all around counter rates and increases. So when you're dealing with counter metrics in Prometheus, you almost always want to compute their rate of increase before doing anything else with them. But PromQL gives you not one or two, but three different functions for telling how fast the counter is going up. And let's be honest, a lot of people are confused by the behavior of those functions, especially around certain edge cases. So in this video, I'll explain to you exactly how they work under the hood, how they deal with all possible edge cases, and give you some recommendations on which one you will want to use. Let's go. So counter metrics are pretty useless in their raw form. Except for occasional resets to zero when a process restarts, they only ever go up. So their absolute value totally depends on when the counter has started at zero and doesn't tell you much about what's going on in the underlying system right now. So what you want to know instead is how fast the counter has gone up over some defined recent time window that you choose. For example, to get the current request rate or the current CPU usage. In Prometheus, there are three functions for calculating the rate of increase for counter metrics. Those are the rate, irate, and increase functions, and each of those functions takes a range vector full of counter time series as an input and returns the counter's rate of increase under that window. So before we look into their behavior in more detail, what's the high-level difference between those three functions? First, the rate function computes a per second rate of increase that is smoothed or averaged over the entire input range window. In contrast, the irate function computes a much faster reacting instantaneous rate by only considering the last two samples under the provided window for its rate calculation. And finally, the increase function behaves exactly like rate, except that it returns an absolute value increase over the provided window rather than a per second increase. By the way, all of these functions need to find at least two samples for each series under the provided window to be able to tell how fast a counter is going up. Otherwise, they will just omit the series from the result. So always make sure that you make your input window large enough to guarantee at least two samples. Okay, let's first have a detailed look at the rate and increase functions together, since they behave almost exactly the same and only differ in their output unit. Imagine that we have a counter metric with a few resets, and we want to calculate its rate of increase at a single point of time. So we select a 5 minutes range window from it that we feed into either the rate or the increase function. The first question that comes up is how these functions deal with counter resets. So we know that counters normally should only ever go up, so we don't want to treat resets as an actual conceptual value decrease and potentially even return a nonsensical negative rate value. So to compensate for resets, we first scan the entire input range for samples that have a lower value than the previous one and assume that any such value decrease must have been a reset. And since counters always start at zero again after a reset, we can then assume that the actual number of increases was at least the value of the sample before the reset plus the subsequent lower value. So we can correct the samples following the reset by adding them to the value we saw before. And we can then do the same thing for all resets under the window to compensate for them as much as possible. We then end up with a series of reset corrected samples that we can now use for the final rate calculation. Just as a side note, this animation shows you what is happening semantically, but the implementation is more efficient and it does not have to generate a full list of corrected samples. Now, compensating for resets won't be perfect since you can still lose increments when a reset happens. Any increments that happen to the counter just before a reset, but that haven't been scraped yet, will be gone forever, and the resulting rate will be slightly too low. But that's usually not a big deal as long as you make sure that resets only happen occasionally and nowhere near the frequency of your scrape interval. Okay, now that we have the reset corrected samples, the rate and increase functions actually don't care anymore about any samples except for the first and the last one under the range. We then calculate the slope between those boundary samples, and that slope tells us how fast the counter has gone up on average under the window. Now, for the rate function, we are pretty much done, and we can just return the slope as a number of increases per second. For the increase function, though, we have to go one step further to give you a good result. If you think about it, in this example, the increase function is supposed to give you the total value increase over a 5 minutes window. But what we can see is that the first and the last samples that we actually have under the window are not 5 minutes apart, but only 4.5 minutes. And that is a common situation, since the selection window will usually be aligned arbitrarily relative to the underlying data. So if we just returned the raw value difference between the first and the last sample, we would really give you a result that is smaller than the real increase that has happened in the underlying system over this 5 minute period. Unfortunately, there's again no perfect solution to this because we do not have scraped samples exactly at the window boundaries. But we can do the next best thing. So assuming that the counter behaved roughly similarly at the window boundaries as inside the window, the increase function now extrapolates the observed slope to the boundaries. You can think of this as pretending as if we had scraped the metric at exactly those points in time. And then we just base the final output value delta on those extrapolated samples. This also means that you can get non-integer results from increase for request or event counters that only have integer increments. That can be confusing at first, but on average, this will give you a more correct result relative to the time window that you asked for. Unfortunately, this extrapolation is less ideal when the counter behavior inside the window is not representative of the behavior around the window boundaries. This can be especially confusing for slow-moving counters that only increment every couple of hours or so. Take a look at this extreme example where we calculate the increase of such a counter over a range window of 1 minute. The extrapolation distance ends up being just as long as the interval between the two samples, so increase returns a value of 2, although there was only 1 increment under the window. Now, that effect will be less extreme for longer input windows, but it's good to be aware of this behavior. And if you've made it this far into the video and maybe even learned something new, please throw me a like and subscribe to the channel. I put a lot of effort into these videos, and this really helps for YouTube to show them to more people. Thank you so much. Now, I also promised you to cover all the edge case behaviors, and there are 2 exceptions where we do not extrapolate the value all the way to the window boundary. First of all, a series may actually start or end halfway through the selection window, in which case we probably don't want to extrapolate it all the way to its respective boundary. Otherwise, we would be producing too many increments. To guess whether a series starts or ends under the window, the increase function looks at the distance of the first and the last samples to their respective window boundary, and if that distance is larger than 1.1 times the average interval seen between the rest of the samples under the window, it extrapolates the slope only half of an average sample interval toward the respective boundary. Also, imagine what happens in this scenario, where a counter begins at a low value under the window and then increases so steeply that we would extrapolate the slope to a negative sample value if we extended it all the way to the beginning of the range window. Negative sample values don't make sense for counter metrics, so we also always cut off the extrapolation at a sample value of 0 as well. Alright, with rate and increase out of the way, let's finally talk about the irate function, which stands for instantaneous rate. Just like rate, irate also calculates the per second rate of increase, but instead of smoothing the result over the entire input time window, irate only looks at the last 2 samples under the window, no matter how many samples you pass in. So you only really need to choose the time window long enough to always select at least 2 samples, but besides that, you get completely identical results for different time windows. And by the way, irate also compensates for resets that happen between those last 2 samples under the window. So this gives you a rate of increase that reacts as fast as possible to your latest values, and that is smoothed as little as possible. That means that irate will give you very spiky results that only really make sense for super zoomed in graphs where you want to see immediate changes in your system's behavior. And you will probably never want to use irate in alerts, since it's always good to have some amount of smoothing and time tolerance in alerts. And in general, out of these three functions, I would always recommend using the rate function unless you have a specific reason to either use irate or increase. That's because rate smoothes the output over the entire input time range, and it also always returns a predictable per second base unit that is decoupled from the size of the smoothing window. If you keep results in base units, you'll generally have an easier time interpreting your results or even combining them with other metrics in PromQL. So I hope this gave you a good idea of how the various counter increase functions work under the hood and how they differ from each other. Let me know in the comments in case you have any questions, and please give the video a thumbs up if you liked it. Also, check out my Prometheus training courses at training.promlabs.com. Alright, see you in the next video, and until then, happy monitoring.